Okay, hanging with Hussick once more. This one we're going to balance redox equations, or balance redox chemical reactions, using what is called the half reaction method. Okay, so I'm just going to lay out the rules, or the steps, if you will, on how to balance redox equations through the half reaction method that I'm about to teach you. So first you split the reaction if you're given a total chemical reaction, a total redox reaction, or if you're given any reaction that you deem is redox. You split it into oxidation and reduction halves. Okay, so you split it into two half reactions. You do this through assigning oxidation numbers. 1, to prove that it's redox, and 2, to determine where's the oxidation, make that a half, where's the reduction, make that a half. Okay, so I'll show you how to do this in subsequent slides. Next, you take each of those half reactions and you balance each one. And you do that using the blue steps that I've laid out here, okay? So to balance each half reaction, you'll see you balance your non-oxygen and non-hydrogens. Then you add water to balance oxygen. Then you add H plus to balance hydrogens. And then you balance the charge by adding electrons. Because in a reduction half reaction, it should gain electrons, meaning electrons should end up on the left-hand side. And in an oxidation half reaction, it should lose electrons, meaning electrons should end up on the right-hand side. And then finally, when you've got your two balanced half reactions, you combine those so that the electrons lost equal the electrons gained. And if they don't naturally balance out in the balanced half reactions, you may have to multiply one or each of those half reactions by a multiplier to make sure that the electrons lost equal the electrons gained. Because that's the whole point of a redox reaction, and that's what makes balancing a redox reaction much more difficult, or balancing a redox equation much more involved and difficult than balancing a regular equation, which is that you've also got baked into the balanced equation somewhere an electron transfer. That's what's special about redox, and that's what makes balancing redox a little bit different. So let's go through one. All right, so let's go through this one. So I say balance the following equation in an acidic environment. Well, first of all, we need to establish, is this a redox reaction? Because if this is a redox reaction, we know we have to use this special balancing method, which I'm teaching you through this video. So, obviously it is a redox reaction, but I want you to be ready to encounter any regular reaction, or be able to pick a redox reaction out of the mix if you're randomly given it on an exam or something. So we first have to just establish, is it redox? How do we do that? Remember, we use oxidation numbers. So we're going to assign oxidation numbers. If they change for any atom from the left side to the right side, that's indicative that this is a redox reaction. So let's go ahead and assign those. So starting with MnO4, we know that oxygen's a -2. If oxygen's a -2, and there's 4 of them, that's a total of -8. And we know that the total charge has to be -1, so Mn, manganese here, must be a +7. Okay, so just a little bit of mental algebra there. Over here, SO2, if oxygen is a -2 like it usually is, then that means sulfur is a 4, +4. Okay, then over here on the right-hand side, manganese 2 plus ion is going to be following the rule where the oxidation number matches the charge of the ion. And then for HSO4 minus, again, we start with oxygen being a -2. We start with hydrogen being a +1. These are kind of golden rules of oxidation numbers. So we just have to figure out sulfur. Okay, so -2 times 4 would be -8, and then it's a -1, so we need to get +7, but then we've already got +1, so this is going to be +6. Does that check out? Yes, I think it does. Okay, so then where do we see differences in oxidation numbers, and where do we see them? Yes, we see manganese here goes from a +7 to a +2, okay? So when the oxidation number goes down, that is reduction, right? So we will write a reduction half reaction over here. So the reduction half is going to be MnO4 minus going into Mn2 plus. So you just write those species that are involved directly in that reduction. Okay, write the whole molecule. Don't just write the Mn, but the whole molecule involved. Okay. Then on the other side of the coin, we've got the oxidation half reaction. So where is the oxidation happening? Well, let's look at changes in oxidation number. You see sulfur here was a +4, and it has become a +6. That's an increase in oxidation number. So therefore, that is oxidation. And we're going to write those species like this, SO2, turning into HSO4-. Okay? Now we're going to balance each of those respective half reactions on their own, and then we're going to combine them in the end. And we'll get into what does this really mean and why is it important that it's in an acidic environment. That's going to come to fruition in a second. Okay, so let's work through. The first thing is you balance the non-oxygen and non-hydrogen atoms. Well, in this case, manganese, there's 1 and 1. Sulfur, there's 1 and 1. Okay? So next, you balance the oxygens by adding water. And remember, you're doing this to each respective half reaction. So we have 4 oxygens here on the left for the reduction half. We're going to need 4 water molecules on the right. Okay, and I'm going to try and color code this. Hopefully it doesn't take me forever, but okay, so we're going to add 4 water molecules on the right-hand side. Right here, like this, 4 waters. Okay? 4 because you have to get those oxygens from water. Each water has 1 oxygen, so you need 4. On the other side, over here in the oxidation half reaction, we actually need 2 waters on the left-hand side. We need 2 extra oxygen atoms, and you should see that you've got 2 extra oxygen atoms on the right because you've got SO4. So we need 2 oxygen atoms there. Now the oxygens are balanced. We're going to move on to hydrogens. And in an acidic environment, like it says, you can just add H plus and leave H plus in the balanced equation. So if it's a basic environment or alkaline environment, you actually have to take an extra step there. We'll cross that bridge when we get there. Okay, but let's add hydrogens to balance the hydrogens we added through water. So for the manganese half, we're going to have to add 8 H pluses. Okay, then just write the whole thing out again. Again, it's a little bit belaboring all the ink we're going to use here, but it's worth it to make sure you keep track of everything that's there. Probably number one mistake I see students make in solving these problems is transcribing incorrectly down the page. In other words, like accidentally copying the formulas incorrectly, or forgetting a charge, or forgetting that it's HSO4 and writing just HSO, it's this kind of thing. So on the right-hand side, we're counting hydrogens. We've got 4 hydrogens on the left, 1 on the right. So we need to add 3 H pluses on the right-hand side of the oxidation half reaction. Okay? Now, what we do is the next step, and if you go back and look, it's add electrons in order to balance the charge. So let's evaluate what's the total charge on the left-hand side of the reduction half. We've got 8 plus, and we've got 1 minus, so that's a 7 plus. What about on the right-hand side? We've just got Mn2 plus, so it's a 2 plus. So where do we add electrons to make that balance? Well, we can only add negatives, right? We can only reduce how positive it is. So if you look at this, we're going to have to add 5 electrons on the left-hand side, aren't we? So let's do it. We're going to put 5 electrons there, okay? And that'll take down our total charge on each side to +2. So copy everything out. Okay, again, make sure you get it right. My stylus is letting me down a little, but we're going to battle. We're going to battle through. And, okay. Of course, it's a little longer than I thought. So this should actually be the balanced half reaction for the reduction side. Okay, we'll check that in a minute because just like I'm prone to making mistakes. Okay, let's have a look at the right-hand side, the redox half. We have no charge at all on the left side of the the oxidation half. We have no charge at all on the left side of the oxidation. Okay, we have a +2 net charge on the right hand side, right? You got a minus there, you got 3 pluses. So we need to add our 2 electrons on the right. Okay, so let's copy the whole thing out and then add 2 electrons on the right. 2H2O. I'm gonna run out of real estate. And then add our 2 electrons. Okay, and if we've done this correctly, this should be the balanced oxidation half. Okay, so let's check, and we can check a few consistencies here. One, are the charges all balanced? Check. On the left hand side here, it looks like, yeah, we end up with what do we end up with? A 1 plus. Wait, what did I do today? Okay, 5 minus. And oh, I know what I did. See, I told you, you gotta check. I accidentally made that a 2 minus in there instead of a 1 minus. So I'm living proof. You gotta check your work. Okay. All right. So now I had this wrong. So we've got 5 minus and 1 minus for 6 minus, so we've got +2 here, and then we have +2 there. Good. Okay. Also, reduction. Reduction is gain, so the electron should be on the left side. Good. Over here, oxidation. Oxidation is lost. We should have electrons on the right-hand side. We do. Check the total charge. It's 0 on this side, and it is 0 on this side. Great. Okay? Now we combine those half reactions to make sure electrons lost equal electrons gained. So I'll show you how we're going to do that. And again, I apologize for all the ink. You can do this a little bit faster, but I'm going to belabor the point because I'm trying to make sure it's really clear how we do this. But we're going to rewrite each half reaction. We're going to stack them on top of each other. Okay? So, and again, in the rewrite, just Jesus take the wheel. I hope I don't make any mistakes, because this is where the mistakes are made. Writing it wrong, transcribing it wrong. Okay. All right, I think I did that correctly. And now electrons lost have to equal electrons gained. Well, how are we going to do that? We have 5 being gained, and we have 2 being lost. Well, you're going to end up using the lowest common multiple of 2 and 5, which is 10. So this is going to be like a 10 electron process, is something you might say. We're going to have to multiply everything here by 2. And we're going to have to multiply everything here by 5. All right? So you're going to end up with 10 electrons, and they're going to cancel, because you're going to end up with 10 electrons, and they're going to cancel. And that's a feature of a balanced redox reaction in the end. It shouldn't have any electrons shown in the balanced overall redox equation, because the electron transfer happens internally. So anyways, back to dealing with the 2 and the 5. Well, this becomes 16. This becomes a 2. That becomes a 2. That becomes an 8. Multiplying by 5. That becomes a 10. That becomes a 5. That becomes a 5. That becomes a 15. Okay. Now, do we have any canceling we can do? I need more colors. More colors. Yes, these 8 are going to cancel with most of these. You're going to be left with 2 H2Os on the left. Okay, these 15 are going to be completely gone. You're going to be left with 1 H plus on the left. Then you've got your 5 SO2s. Those aren't going anywhere. Then you've got your 2 MnO4 minuses. Okay, so that's the left side. Just double checking my math. I'm doing this in real time. Okay, then we've got 2 Mn2 plus over here. And we've got our 5 HSO4 minus over there. And that could be it. So let's just double check that. Again, best way to check all the charges. Check all the charges and make sure the charges are balanced, and then you can look for the atoms being balanced like you would for any other equation. So we've got a +1 and we've got 2 minus. So this is a -1 over here. Check over here, we have two pluses, so that's +4, but we have the 5 minuses for a -1 over there. Looks good. Then you can just check 2 manganese, 2 sulfurs, etc. 5 hydrogens. Yes. We have done it. This is the overall balanced redox equation. See? A lot of work, but I'm belaboring it. You could work a little faster than that. I'll do another example where rather than being able to have H plus in the end, we would have hydroxide OH minus in the end because it's a basic environment. So I'll show you that basic one next. Okay, let's do this one. I actually find this fun, which is maybe a little bit sickening, but join me. Okay, balance the following equation in a basic environment. So I'm going to show you how it's a little bit different if it's in a basic environment to begin with, but follow all the same steps. I'm hopefully going to work a little bit faster. Is it, I got to get the right pen going first. Is it redox? First of all, you want to confirm that. And you need to do oxidation numbers anyways, because you have to establish what's the oxidation and reduction half. So hydrogen's a +1, oxygen's a -2. There's 3 of them. That's going to be a total of -3. So bismuth over here, Bi, is going to be +3. Then you've got over here, oxygen's going to be a -2. The whole thing. So tin's going to be a +2 because -2 times 2 is -4. It all has to be -2. Oxygen here is going to be a -2 times 3 would be -6, which means that's +4. Again, if you're struggling to figure out how you know this, take a minute, go back and review oxidation numbers. You have to do a little bit of algebra here. Okay, and then bismuth, we're assuming here is its pure elemental form. It doesn't show it, or maybe it did and I just didn't write it, but it's bismuth solid. It's a metal, so it's going to be a 0. And so if we look at where the changes are at, boom, bismuth goes from a +3 to a 0, which means that is the reduction half, right? Okay, because reduction is a decrease in oxidation number, so we're going to write those species involved there for the bismuth half. Then on the other side of the coin, we are going to find out where the oxidation half is. So let's have a little goosey gander. And we see that for tin, it goes from a +2 to a +4. An increase in oxidation number. That means oxidation. So we're going to write that oxidation half. It's tin. What is this? Tin oxide going to, I guess I'm supposed to write tin dioxide going to tin trioxide ion. So I don't know what it's called. It's an ion. Polyatomic ion. Okay, go through the balancing as you would if it were acidic, and then we make a little bit of a tweak for the basic thing. So bismuth, good. We need 3 waters. Again, I'm just going to kind of scribe this in here quickly. We need 3 water molecules to balance out those oxygens. On the other side, tins are balanced. We need 1 extra water molecule here to balance out that oxygen. And you may think to yourself, well, why are we allowed to just judiciously add water here or there? Obviously, this whole thing has to happen in a watery environment. It has to happen in an aqueous environment. And the fact that it's basic as well, that's also kind of telling you it's got to be wet. Okay, it's all a part of it. All right, so we've done the oxygens. Now we're going to fix the hydrogens. Well, over here we've got 3 times 2 for 6, and over here we've got just 3. So we need 3 H pluses on the left-hand side here. Okay. And that will sort the hydrogens for the reduction half. Then over here we need 2 extra hydrogens on the right. So again, even though it's basic, we're going to temporarily add H pluses, and then we're going to get rid of them because they can't really be there. If it's if it's a basic environment, you can't have H plus floating around. That is a characteristic of an acid. So what do? Well, to deal with this, you actually add hydroxides on both sides to cancel them out, okay? So we're going to add 3 hydroxides over here, and then we're going to add 3 hydroxides over there, all right? So the net effect is these become water, right? So you end up with 3H2O over here. And then you've got the hydroxides on the other. So let's check out this side. We're going to add 2 hydroxides here. Those are going to cancel and make 2 waters. Okay? And then we got to do unto the left whatever we do unto the right. So we're also going to add 2 hydroxides there. Okay? So I'm going to rewrite those now with the net changes. So the other thing is that if you look at this, on the redox half, those 3 waters are going to cancel with those 3 waters. So now we've got just like this. Bismuth hydroxide goes to bismuth plus 3OH minus. And baked into that, the hydroxide should balance. Like the hydrogen should balance and the oxygen should balance. And you can see that that's the case for that reduction half. Let's see if we did this right over here. So this water now, here is going to cancel with one of those waters. So we're going to have 1 water on the right. So this is going to end up being like this. And then we'll just check that we're doing it right. Okay. So have we got the oxygens balanced? 4 and 4. We've got the hydrogen still. Okay, great. Now we're on to the part where we balance the charges with electrons. Okay. So you can see for the reduction half, we're going to need 3 electrons on the left, aren't we? Because we have a 3 minus on the right-hand side, and we're going to make both sides have a 3 minus charge. Looks good. Reduction is gain of electrons, so that's also consistent. So I think what we've done there is we have a balanced reduction half. Let's go over here to the oxidation half. We should be adding electrons to the right if things are going right. 2 times minus 1 is minus 2, minus 3. So we're going to add 1 electron on the right-hand side. Consistent with oxidation, because oxidation is loss of electrons, so it should end up producing an electron or 2, as it does. Okay, so then if you look at this, that should be the balanced oxidation half. In the end, we combine them, remember, and we want to make sure that the electrons lost equal the electrons gained. So you can stack those up on top of one another. I think I'll do it that way, even though it's going to take me another minute and the video is going to get a little bit longer, and that's going to make people not so happy. But just play it on 2 times speed or something, and that's going to be the ticket. Okay. So here we go, here we go, here we go, here we go. Da-da-da-da. Don't make a mistake in the transcription. How many times are they going to mention that? Okay. Electrons lost equal electrons gained. Lowest common multiple of 3 and 1 is 3. So we're going to multiply everything in the oxidation half by 3. So that's going to become 6. That's going to become 3. 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 Electrons are now going to cancel. Okay? And what else can we cancel? We're going to cancel those hydroxides. We're going to have 3 hydroxides over there. And that is about it. Let's write the final thing. 3 hydroxides plus bismuth hydroxide plus 3 SNO2 minuses turns into bismuth solid plus 3 SNO3 minus plus 3 H2Os. And no electrons in the final thing. That is good, because in a final balanced redox equation, you don't have any electrons. And go back to the start, this should have been done in a basic environment, and in fact, yes, it was. We see we have hydroxides in the end. Final thing to check, just double check, because, and I'm talking to myself as much as anyone because I make mistakes, check the charges. If the charges line up, that we know we've done it right. So you can see here we've got 3 minus. I'm going to choose a color here and maybe highlight this for you. Here you go, we got 3 minus, okay? And we have 3 more minus, so that's a total of minus 6 over there. And then on this side, we have 3 and 2 minus, so that's a total of minus 6 over there. Looks good to me. And if you can follow through this and practice, 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 you'll be masters at balancing redox equations. Thank you so much.